Hi, this is Dr. Collins Jones. Welcome to segment 10, the final segment of my video series on measurement, significant figures, and basic data analysis. In this segment, we will cover descriptive statistics and the Q-test. Recall from segment 9, the Q-test is the test we use to determine if a data point is an outlier and whether or not we can keep it or reject it. In this segment, we will work through several examples. But first, let's just review what basic descriptive statistics are. We'll start with the mean or average, which is represented by the symbol X bar, that is an X with a line over it. The average is a calculated number that represents the center of a data set, or it is the typical value for a number of replicates. So the average is determined by, or calculated by, the sum. This sideways W is actually a capital sigma, which just means the sum of, or add together. So we're summing, adding all of the different measurements together from the first measurement to the nth or last measurement, and we're dividing that sum by the total number of measurements. So this n in the denominator is the same as the n at the top of the sigma. So if I had, for example, 6 measurements, 6 unique measurements, then I would say x1 plus x2 plus x3 plus x4 plus x5 plus x6 divided by 6, the total number of measurements. So the average is what we report, and it is used as the experimental value in calculating the percent error. So when we do a protein assay, a nucleic assay, we do an enzyme assay, and we do replicates of it, we determine the value for each replicate, and then we determine the average, and it is the average that should be reported in your final report or on the SOP or the batch record. The standard deviation is represented by the lowercase Greek sigma. So this little O with the line coming out the top is the lowercase sigma in Greek. The standard deviation measures your precision. Remember, how close your values are to one another, or how the data points are dispersed about the mean. You know, they above the mean, below the mean, how much scatter is there away from the mean. So the standard deviation is calculated by taking the square root of the sum of each individual data point minus the average squared, divided by the total number of data points minus 1. Okay? Then we have the Q-test, and the Q-test is a test, again, which allows you to reject true outliers. So no longer do you just have to guess. You can actually determine if a suspect point is an outlier or not. To do the Q-test, we first have to calculate a Q value, right? So this is called Q-calc, and Q-calc is the absolute value of the suspect value minus the nearest value. So the suspect value is the value you think is the outlier, and the nearest value is the data point that numerically is the closest to the suspect value. And then this is divided by the largest value minus the smallest value, and one of these, either the largest value or the smallest value, will be the same as the suspect value. So this gives us a number, the ratio, and we compare the calculated Q value to the Q critical value, which is given in a statistical table. And then if the Q calculated value, that is from the data we actually have, is greater than the Q value in the table, we reject the value as an outlier. If it's less, if the sign is reversed and Q critical is greater than Q calculated, then we must retain the value. We can't discard it. The percent error, again, is how close your measured value is to the true value. We did several calculation examples of this in segment 9, so I'm not even going to put the equation up, but hopefully you remember the equation from segment 9, because we will include this in our examples. And then finally we have the percent CV, the percent coefficient of variance. This is a measure of how consistent the operator is in obtaining measurements. The lower the percent CV, the more consistent and reliable the person making the measurements is. So the percent CV is calculated by dividing the standard deviation by the average. So standard deviation is the numerator, The average value is in the denominator, and then we multiply this by 100%. So what we're going to do from here on is just work our way through a couple of examples. So first, let's just calculate the average and the standard deviation. So I've given you a data table here of protein concentrations, right? So these are supposed to be replicates. Protein concentration is indicated here in milligrams per mil. So we have 8.94, 8.75, 9.25, 6.90, and 8.83. So first task, calculate the average. So the formula, again, to calculate the average is x bar is equal to the sum of each individual data point divided by the total number of data points. Okay, so this just means add all these values together and divide by the total number of measurements that you made, right? And so just to sort of put this in the context of our math equation here, 8.94 is x1, 8.75 is x2, 9.25 is x3, 6.90 is x4, and 8.83 is x5. So we just plug this into our equation and we get 8.94 plus 8.75 plus 9.25 plus 6.90 plus 8.83. There's 5 measurements, so we're going to divide by 5. Note, this 5 is a counted or exact number, so it is not used to determine the number of significant figures. Essentially, this has an infinite number of significant figures. So we do our calculator, run this through the calculator, we get 8.534. But notice each of these is only 3 significant figures, so we need to round this off, right? The last significant digit then, if there's 3 significant figures, is the 3. The next digit over is a 4, so we retain the 3. So we have 3 significant figures. The standard deviation is 0.93, and in this segment, for our purposes, I'm going to assume that you're able to do these basic descriptive statistics on your calculator using the statistics functions on Excel, on GraphPad Prism, if you have access to that, or on whatever other statistical platform that you have, but you are able to actually calculate the standard deviation without having to do it manually. So we would report this as the average plus or minus the standard deviation. So this would be 8.53 plus or minus 0.93 milligrams per mil. Okay? Let's calculate then the percent coefficient of variance. So it's going to be the standard deviation divided by the average times 100%, or 0.93 divided by 8.53 times 100%, or our percent CV is 10.9%. Okay? But if you noticed, I was a little worried about the 6.90. This looks to me like it's an outlier. It's roughly 2 units below any of the other, less than any of the other measurements. So let's test that. Let's identify any possible outliers in the data set below and use the Q-test to determine if the suspected outlier should be retained or rejected. All right, so again, here are our numbers. We're worried about 6.90, so we're going to apply the Q-test. And that would be the first thing we do, really, is determine whether or not anything is an outlier before we calculate the mean and the standard deviation. So first thing we do, identify the largest and smallest numbers in the data, 9.25, 6.90. Okay, and there they are. So now let's enter the values in the formula to determine our Q calculate. So it's going to be the suspect value, 6.90, minus the nearest value. So what's the next smallest number in this data set? And it looks like it's 8.75. So it's going to be the absolute value of 6.90 minus 8.75 divided by the largest value, 9.25, minus the smallest value, our suspect value. We do the math on the calculator, and we end up with this number. Our Q calculated, or our calculated Q value, is 0.787. Okay, so now we need to determine, is our calculated Q value greater than the critical Q value listed in the table over here? or is it less than that? Right? So we have 5 measurements, right? 1, 2, 3, 4, 5. So we're going to look at n equals 5. And remember, I said we do this at the 95% confidence interval. Okay, so our critical Q value is 0.717. If our number is greater than this critical value, then we have to reject it because it is an outlier. So we just put these in. You put in 0.787. Okay. There we go. And we put it and we compare it to 0.717, and we see that in fact 0.787 is greater than 0.717. So that means that 6.90 is an outlier. It can be rejected or discarded. And this measurement, 6.90 milligrams per mil, will not be used in the calculations. So we put an X through it. Okay. All right. So that means we're now going to redetermine the average, omitting the outlier. And again, we would actually determine if a number is an outlier before we do any calculations of the average or the standard deviation. The first thing to do is to identify and decide whether or not an outlier should be retained or discarded. So now we're going to redo our calculation. 8.94 plus 8.75 plus 9.25 plus 8.83. So we've discarded the 6.90, and now we only have 4 values that we've added together. So we do that on our calculator. We're 8.9425, but now we have to have 3 significant figures again, and the 4 is the last significant digit. It's the uncertain digit, so the next digit over is 2, so we retain the 4. And our standard deviation calculated as before with your calculator, Excel, GraphPad, Prism, whatever. Okay. So our reporting form again is going to be the average plus or minus the standard deviation. So this would be 8.94 plus or minus 0.22 milligrams per mil. And if we calculate our percent CV, now this is going to be the standard deviation, 0.22 divided by the average times 100%, or 2.46. And since we're able to discard the outlier, we see that our percent CV has decreased, right, from 10% to 2.5%. So that's pretty good. That means this is now a little bit more reliable. Okay, let's do a complete statistics calculation. We're going to sort of put everything together here. So suppose I did a 1-to-9 dilution of 4 replicates and obtained the following absorbance values. Maybe this is just to test the status of the spectrophotometer. So I get 0.712, 0.699, 0.585, and 0.705. And from this data, from these 4 data points, we want to first identify and confirm any outliers. Remember, we always try to figure out if there's outliers before we do any of the rest of the calculations. Then we calculate the average and standard deviation, then write the values in the report form, determine the percent coefficient of variation, and then if the accepted value of the absorbance is 0.689, determine the percent error from this set of measurements. So first, use the Q test to confirm and discard suspected outliers. So take a minute, look through this data. What do you think could be an outlier? Right, 0.712, 0.699, 0.585, or 0.705. And I think that 0.585 is probably an outlier. So I'm going to call that my suspect value. I suspect it is an outlier. So we're going to identify the largest and smallest numbers, 0.712 and 0.585. We're then going to apply this to our formula to calculate the Q value for our data, the absolute value of the suspect value minus the nearest value divided by the largest value minus the smallest value. So if we plug those numbers in, we get a ratio of 0.898. So that's our calculated Q value. We now need to compare this to the Q critical value in the data table. So here's the data table again. And now we have 4 values. So we're going to look at n equals 4, and again, the 95% confidence interval. Okay, so our critical Q value is 0.831. If we are greater than 0.831, we need to reject this. So we put the two together and make the comparison, and 0.898 is in fact greater than 0.831. So that means 0.585 is an outlier. It can be rejected or discarded, and we will not use this measurement in the calculations. So again, I've just put an X through it to indicate that. And you could actually make a little footnote here that says rejected based on the Q test. Okay, calculate the average. Right, we know how to do this. Add the measured values, divide by the number of measured values. So, and now we're excluding the outlier. So this is just going to be 0.712 plus 0.699 plus 0.705 divided by 3. Okay, and our average value is 0.705. 3 significant figures. Calculate the standard deviation as before. Okay, and the calculated standard deviation comes out to be 0.0065065. But rounding that up, right, we're only going to go out to the third place past the decimal, the 6. The next digit over is a 5. When it's a 5 or higher, we round up. So our standard deviation will be 0.007. Okay, 3 places past the decimal. So now we're going to put this in report form. The average plus or minus the standard deviation, 0.705 plus or minus 0.007. Okay. The percent CV, not bad. 0.007 divided by 0.705 times 100%. It's just a little under 1% CV. And then calculating the percent error, remember our true value, right? Accepted value, true value is 0.689. So we're going to plug this into our percent error equation, true value minus experimental value, divided by the true value times 100%. And when we do that, our percent error is minus 2.32%. Okay, so let's do another problem, right? Calculation number 2, sorry. The following densities were determined for complete cell culture media. So sometimes we have people determine the density of the cell culture media so that we know what volume to add or what mass to weigh out to get a certain volume when we put it into the bioreactor. So we determine the density because we can convert volume into mass, and that tells us how much to weigh to get a certain volume of media into the bioreactor. But to do that, we determine the density experimentally by just taking various volumes and weighing them and then calculating the density as grams per mil. So we've already determined the density. First thing we want to do is identify and confirm any outliers with 95% confidence, calculate the average and standard deviation, write those values in report form, calculate the percent CV, and if the accepted value for the media density is 1.12 grams per mil, determine the percent error. So let's look at the numbers. We have 1.11, 1.08, 1.03, 1.05, 1.09, 1.09, and 1.07. So we have a total of 7 values here. So again, first thing you always do is identify what you suspect to be an outlier and then determine using the Q test whether it is an outlier or not. So actually for me, there's 2 potential outliers here. One is 1.11 and the other is 1.03. I'm only going to demonstrate how to do the Q test for the 1.11 just because of space limitations and because by now, hopefully it's repetitive to you. So we're going to use the Q test to confirm and discard or retain any suspected outliers. So our largest value is 1.11. Our smallest is 1.03. Enter these values in the formula to determine the Q calculated. Okay, so if we do 1.11 minus 1.09, that's the nearest numerical value, divided by 1.11, largest value minus 1.03, the smallest value, we get a ratio, a Q calculated of 0.25. So the calculated Q value is 0.25. We then want to compare this to the critical Q value listed in the table. Okay, so we have 7 measurements here. So this is going to be N is 7 at 95%. Okay, and so 0.568 is our critical Q value. We're going to compare Q calculated to Q critical, and we have 0.25 is less than 0.568. So we must retain 1.11. It is not an outlier. It cannot be rejected or discarded. We have to use this measurement in the calculations. And if you go back and do the same calculation for 1.03, it turns out that 1.03 is not an outlier. It also must be retained. So we're going to retain the 1.11 and we're going to retain the 1.03. The Q test tells us that we cannot reject either of those numbers. So knowing that, let's calculate the average. All right. And again, it's just the sum of each measurement divided by the total number of measurements. So here we have 7 measurements, and then we calculate the average. We get this long number, but we only have 3 significant figures. So we're going to have 1.07. 7 is the last significant digit, and the next digit over is 4. So we retain the 7. So our average value is 1.07 grams per mil. 3 significant figures. Calculate the standard deviation. And again, the standard deviation, after we do the round off, right, it's going to just be 2 places past the decimal point. So it's going to be 0.03 because we added 2. That's our significant figure. But after that, the next digit is a 6. So we're going to round up. Okay, so reporting this, 1.07 plus or minus 0.03. Our percent CV is 2.80%. And then our percent error is going to be the true value, which is 1.12 grams per mil minus the experimental value, which is our average value, 1.07 divided by the true value. So plug that in, do the calculation. We have roughly a 4.5% error, right? Or 4.46% error. Okay, so to summarize this, the average is the sum of the measurements divided by the total number of measurements. The final result is reported as the average plus or minus the standard deviation. Outliers are measurements that appear to be far removed from the other measurements. They're either too low or too high. The outlier is assumed to be the result of an erroneous measurement, either instrument or operator error. Outliers can be tested, and they can be retained or rejected based on the results of the Q test. But wait, more statistics await you. Not in this segment, but I encourage you, if you're going to go into the life science, whether it's research or whether it's industry, that you take a full semester statistics course, right? Statistical analysis is important in summarizing and evaluating experimental results, which is sort of what we did in this segment. It's important in the design of experiments. There's a whole field now called DOE, design of experiments, where statistically you can change multiple variables at the same time in an experiment and still get meaningful data and decide what's important and what's not. And then, of course, statistics is important if you're into the quality control field and quality management systems. And so here, this chart just shows you that you collect your data and then you may ask different questions, because what we didn't cover in this segment was how to compare 2 very different experiments, like experiments over time, experiments at different doses of a drug, experiments of different production runs. All right, so this is a whole nother set of statistics. And honestly, this is one of the reasons I really like GraphPad Prism, because GraphPad Prism is an intermediate level statistical software. It's really easy to use, and it guides you through the tests that you should be making based on the data that you have. So for example, if your standard deviations are far apart, you really shouldn't use a t-test. It will suggest the appropriate test to use based on the data that you get. All right, and that is the end of segment 10 and the end of this video series. I hope you found it helpful. Bye.